next application of integrals we're going to look at is finding volumes. And we're going to start with a very basic shape that you're familiar with and discuss the idea behind this technique. So, a cylinder can be thought of as a bunch of circles stacked on top of each other. The volume of the cylinder would be, you may have seen it written this way, you may have seen it written this way. But the idea is that you find the area of the base, which is what this capital B stands for. And then once you know that area, you multiply it by the height, stacking all of these slices together, and that gives you the volume. We can either write capital B, which represents the area of the base, or we can use pi r squared because the base is a circle. If the shape of the cross section of the 3D figure is known, so the cross section being in this case a circle, we can set up an integral for the area formula, and this will give us the volume of the figure. When you integrate area, you get volume. And if you just think about that for a second, area, for instance, if we wanted the area of the square, we would measure that in perhaps inches by inches or inches squared. And then when we talk about volume, in the same situation, the units would be inches cubed. And you can see how this mirrors integration, where if we know the area, which has an exponent of 2 on it, when we integrate, the exponent becomes 3. We increase that exponent by 1. So you can see how the idea of integration is kind of built in. The first type of solid we're going to look at is solids of revolution. All a solid of revolution is a solid created by taking a function, such as the one you see in this first graph, rotating it around an axis, which kind of creates this cone shape that you see in the second graph. Just to give you a better visual on this, I'm going to use Mathematica. I asked Mathematica to take the same function that generated the picture that you just saw and graph it first. Now this looks a little bit different just because the scale is different, but it is the same function as the graphs we were just looking at. And now that I've asked Mathematica to do that, I can use the next command to have it graph the 3D shape. So what's neat about this is you can now rotate this around. You can see the actual shape that we're trying to calculate the volume of. This shape looks hollow, but remember, we're making a solid of revolution, so you want to imagine it not having that opening. Now, the idea for how we're going to find the volume of this is to imagine slicing this shape up into very thin slices. And like we saw previously when we were estimating the area under a curve, when we sliced it up into rectangles, the more rectangles we use, the better the approximation got. It's the same idea here when we talk about slicing the shape into discs. If I slice this shape into 5 discs, it looks like this, which is not quite as smooth a curve as the original. You can see if I increase it to 10, now this shape is in fact looking more like the original. I can increase this number further still, and you can see that by increasing our number of slices, we are approaching the actual volume of the object. So that's the idea behind this technique. The same way that we used integrals to sum up rectangles and thought of it as a limit, we're going to do the same thing here. We're going to use the integral to take the limit of making these thinner and thinner and thinner slices. So when we rotate a function around an axis of revolution, you're going to notice that that will always form circular cross sections because it's made by a rotation. And so therefore, we are always going to be using the area formula pi r squared to represent the area of one cross section. And then, as you saw with the cylinder, we're going to multiply the cross-sectional area by the height of that slice, which is going to be dx, and we're going to sum up all those slices using the integral. When we have a horizontal axis of revolution, as we saw with the cylinder, in order to get the volume, we need to integrate the area of a cross-section times the width of that cross-section which is going to be represented by dx. And by taking the integral, we're taking the limit of the approximating sum of adding up all those individual slices. Now, because our cross section is always a circle, that means we're going to be integrating pi r squared times dx. And if we're integrating with respect to x, this would mean I need to write the radius in terms of x. So now we'll look at how to do that. This is an example not in your book, but we're going to find the volume of the solid, and this is the one we were just looking at in Mathematica, that was created by revolving the region bounded by the function y equals x to the 1/3 power and the x-axis on the interval 0 to 6 about the x-axis. Now it is helpful to have a graph to look at, and this picture above is the graph of the cube root function, and it's going from 0 to 6 in this particular case. So I'm going to begin by saying, okay, if I want to find the volume, I'm going to integrate the area of a single circle, which is pi r squared, times the width of my slices, which is dx. I'm going to line up these slices all the way starting at 0 and ending at 6. So those are my limits of integration. Now, as we said before, I can't integrate with respect to x if my variable here in my function is r. So I need to think about how to write the radius in terms of x. The radius is changing depending on where each individual disk is located. For instance, if you slice the shape back here at the beginning, the radius is only this long from the axis of revolution to the function. But if you move further out to a different x value, you can see the radius gets bigger. And here, the radius is even larger. So the radius is not remaining constant, so it shouldn't be a surprise that we can write it in terms of the variable x. And how we do that is, it is this function that is controlling the height, or in other words, the length of this radius. Back on this little circle, whatever y value corresponds to this point is going to be the length of the radius. And the y value is being determined by the function y equals x to the 1/3 power. So if this happened to be located at the value 1, I could take 1, put it into the formula, it would give me the y coordinate, which would be the radius. The same thing holds true down here. Whatever x value this is located at, the y coordinate is being generated by this function. So the radius here is going to be x to the 1/3 power. And the same thing is true here at this x value. So because it is that x to the 1/3 power function that is controlling how tall the radius ends up being at any given x value, my radius can be written as the function x to the 1/3 power. So I now go back to my integral. I'm going to substitute that in place of the radius, and I need to not forget that there was a squared on the radius, so I need a squared there. And now my integral is entirely in terms of x. I do a little simplification where I pull my constant out in front, and when you have a power raised to a power, you multiply those exponents, so I have x to the 2/3 power. Now you would just integrate using the power rule and then your fundamental theorem of calculus. Now, once you do enough of these, it is a little bit more efficient if you kind of think ahead. I know if I substitute 6 in to my antiderivative, I know what that's going to look like. It'll be 3/5 of 6 to the 5/3 power. And then I am supposed to subtract what I get when I substitute 0. But if you think about it, if I raise 0 to an exponent, it's going to stay 0. And then it multiplies a number, and so it's still going to be 0. So rather than take the time to write out that full substitution, subtracting 0 will not have an effect, so I can just get rid of that right away. And this is what I need to be typing into my calculator to get a decimal approximation for the volume. This one turns out to be about 37.344. Because this is a volume that's being measured in units cubed. So that's the volume of this cone shape. Now, if you change your axis of revolution so that it's vertical, then it makes much more sense to integrate like from here to here in this first picture, from A to B. We're creating circles centered around the y-axis. And so we're stacking those circles from the bottom of the graph at y equals A to the top of the graph at y equals B to find our total volume, which means I want to express my whole integral in terms of y. So to find the volume, when you rotate around this vertical axis, the cross sections are still going to be circular. So we're going to need to find the area of those cross sections in terms of y and integrate with respect to y. Because the cross sections are circular, that means we're going to integrate pi r squared dy, where this r is in terms of y. So here's an example not in your book. We're asked to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, x equals 0, and y equals 5 in the first quadrant about the y-axis. It's going to be helpful to have a graph here. Your graphing calculator, please realize, won't be able to graph x equals 0, but that is just the y-axis. You can also do this by hand, or I'm going to use the website desmos.com. So I have put the three equations into Desmos, and you want to bear in mind we're only interested in the shaded area that's in the first quadrant. So if you look for the area bounded by these three functions, that's this region right here. So we're going to take this region, we're going to rotate it around this axis and create, again, another cone sort of shape, but this time it's vertical. So you want to have this basic picture in mind as you go ahead and perform the integration. So now to set up this integration, I will need to integrate the cross-sectional area, which is represented by a circle, pi r squared, but this time in terms of y. My limits of integration, I want to be thinking in terms of the y values. So where does the cone shape begin and where does it finish? You'll notice that's from 1 to 5. Make sure you're using y values for the limits on a y integral. All right, if I'm integrating in terms of y from 1 to 5, that means my cross sections are going to be circles that are going to kind of line up like this. So when I'm looking at the radius at any given y value between 1 and 5, I'm looking for this distance from the axis of revolution to the edge of that circle, which lies on the function. The name of this function was, again, y equals x squared plus 1, but it would not be accurate to say that the radius, therefore, is x squared plus 1. That's because, remember, the radius needs to be in terms of y. I'm going to need to take this function, which is solved for y, and solve it for x. Now there's a very important step that has to happen here. To get rid of the squared on the x, we of course want to take the square root of both sides. However, when you introduce that square root, you must remember there's always a positive and a negative root. So in other words, I have plus or minus the square root of y minus 1. And that's important to remember because each of those generates one branch of what we're seeing on the graph. X equals the positive square root of y minus 1 is this part of the function that's actually in the first quadrant. And I know that because if x is in the first quadrant, it's going to be positive, so I'm going to get a positive square root. The other possibility is that you could get a negative output. So that's the equation for this left-hand side, which ends up in the negative x values, because you can see x equals negative square root of y minus 1. You're going to be in the negative side. So for this problem, all I actually care about is this portion that's in the first quadrant. Therefore, the function that is controlling the length of the radius is right here. So in other words, my r is going to be equal to the square root of y minus 1. I'm going to substitute that into my integral. Simplify, and something nice happens right here. When you square the square root, you do just get y minus 1, which again is a very simple integral to integrate. If you work through the fraction work here and simplify this, that will all condense to just 8. So our final answer is actually 8 pi, or it's totally fine if you give the decimal equivalent. So that's how you integrate using disks. And again, it's not very different between integrating horizontally or integrating vertically. You just have to make sure that you're using the right variable in your integral and you're good to go.